Hi everyone, thanks for coming to our presentation, Discrete Optimization for Shape Matching. This is a collaborated work with Simona Mauzi, Peter Wonga, and Max Ovsyannikov. In this paper, we propose a discrete solver for shape matching problem. We are interested in automatically finding correspondences between shape meshes. Shape matching is an important problem in computer graphics, and it has a lot of applications, such as shape analysis, motion transfer, and so on. The shapes we are dealing with are discrete triangle meshes, such as the two head shapes shown here. Our goal is to find a meaningful point-to-point map between the two triangle meshes. For example, we would like to map a vertex on the nose x1 to the vertex y1 on the target shape. Similarly for the vertex on the ear and chin. We use a color transfer to visualize the correspondences. If two vertices are corresponding to each other, we will assign them with the same color. We use a subscript to denote the map directions. For example, T12 means a pointwise map that maps the shape S1 to the shape S2. Existing methods for shape matching can be roughly categorized into four groups, including the point-based methods, parameterization-based methods, and methods using optimal transport formulation. Our work uses functional map representations. This technique tries to find correspondences between functions defined on the shapes instead of finding correspondences between the vertices directly. A standard functional map pipeline can be divided into two main steps, the functional map initialization and pointwise map refinement step. Specifically, for a given shape pair, we first use existing methods to compute a few pairs of shape descriptors. We can define some energy E of C based on the descriptors and some other geometric constraints. Then a continuous solver is used to minimize this energy and output a functional map C. We can recover a pointwise map pi from the functional map C by a discrete conversion step. Usually, this recovered pointwise map is not in great quality, and different post-processing techniques are proposed to improve its accuracy, smoothness, or even bijectivity. There are two major observations of this pipeline. First, different energies are used for the functional map initialization step and the pointwise map refinement step. Second, usually a functional map is optimized with regularizers, but without hard constraints. This can lead to undesirable local minima. For example, if we optimize the commonly used Laplacian commutativity energy without any hard constraint, the global minimum is zero matrix. To address these issues, we introduced the concept of proper functional map. We then regularize the functional map optimization in the space of proper functional maps. We propose a discrete solver to efficiently deal with this hard constraint. Finally, we show different evaluations and applications of our discrete solver. We first introduce the concept of proper functional map. A functional map is proper if it arises from a pointwise map, which means if there exists a pointwise map pi such that this equation colored in blue holds. Here phi, they are the Laplacian Beltrami eigenbases of shape S. We can collect all these proper functional maps and denote the corresponding proper functional map space as P. Note that this space is discrete and exponential in size, since it consists of the functional maps that arise from pointwise map. Let's first take a look at the proper functional map space. In the middle, we show the proper functional map space P between a pair of head shapes. We can see that each proper functional map has an underlying pointwise map as shown on the top right. In the standard functional map pipeline, there is a conversion step that the pointwise map is recovered from the optimized functional map. This step can be equivalently formulated as projecting an arbitrary functional map into this space P and finding its closest proper functional map in this space. For example, a ground truth functional map is derived from the ground truth pointwise map correspondences. It is already a proper functional map, therefore the projected proper functional map is itself. For a random functional map, it can be far from proper. We can see that the projected proper functional map is very different from the original one. In this example, we show the optimized functional map from the standard functional map pipeline. We can see that this is very different from its projected functional map. This shows that the standard functional map optimization without any hard constraint can lead to a functional map that does not have an underlying pointwise map, and the conversion step, which is the projection step here, can introduce some errors. This motivates our formulation that it is important to solve for a proper functional map during the optimization. In the standard functional map pipeline, as discussed before, we usually optimize a functional map without any hard constraint. This is easy to solve, but the output functional map is usually not proper, which means the optimized functional map does not correspond to a pointwise map directly. In 2017, the multiplicative operators are proposed to guide the functional map optimization process towards proper functional map. Since this new term is introduced as a soft regularizer, there is still no guarantee to obtain proper functional map in this way. In our work, we propose to optimize a functional map in a constraint setting. As highlighted in red, we always constrain the variable functional map C to be proper. The advantage of our formulation is that we can guarantee the output is always a proper functional map. Therefore, our goal is to optimize any given functional map-based energy with respect to the hard constraint that the functional map should be proper. We can immediately come up with two naive solutions. The first solution is to ignore the hard constraint for optimization and then project optimized functional map to make it proper. Actually, this is a standard functional map pipeline with an extra projection step. As discussed before, it can lead to undesirable local minima, such as zero matrix, and the projection step can introduce some errors. Another naive solution is to enumerate all possible proper functional maps, since the space is discrete, and then find the global minimizer. However, the proper functional map space is too large, and this exhausting searching only works for shapes with less than 10 vertices. In our work, we propose an efficient discrete solver. It consists of three main steps. We first reformulate the given energy by replacing some term C by the proper functional map constraint. We then add a coupling term between the functional map and the newly introduced pointwise map. We call this modified energy as a relaxed version of the original energy. During the reformulation and adding the coupling term, we make the functional map and the pointwise map free variables of the resulting problem. We can then alternatively solve for pointwise map and update the functional map from the pointwise map to make it proper. Note that in the last step, we can also apply zoom out and sampling techniques to further improve the efficiency and accuracy. To make this pipeline possible, the key step is to relax the original energy in a way that allows efficient point-to-point map recovery. This relaxation relies on the following lemma, that for arbitrary matrix X and Y, and a reduced and orthogonal basis phi, we can construct two problems. The first problem can be derived from many functional map energies. The second problem is in a simpler form, which is row separable and can be solved in closed form solution. We show that these two problems are equivalent to each other. Please see our paper for the corresponding proof and additional discussions. This lemma inspires us to reformulate the original energy in a special form that can be solved efficiently. Here is an example that we want to minimize the descriptor preserving energy. F1 and F2 is a pair of given shape descriptors, and C is a variable functional map. Our discrete solver works in the following way. We first reformulate the descriptor preserving energy by replacing the functional map C by the proper functional map constraint as colored in red. This modified energy actually only depends on the newly introduced pointwise map. We then add a coupling term between the functional map and the pointwise map with weight alpha as colored in red. This term is to make sure the pointwise map should be coupled or related to the proper functional map we are solving for. We can see that this relaxed energy is in a simple form according to our lemma, and the pointwise map can be solved in a closed form solution. We then update the functional map from the optimized pointwise map to make it proper. Here is an illustrative example of minimizing the descriptor preserving energy we just discussed. In the blue box, we show three different pairs of input descriptors. In the red box, we show how the descriptor in the source shape get transferred to the target shape over iterations using our solver. The last column shows the underlying pointwise map of the optimized proper functional map. We can see that in this case, the final pointwise map respects the correspondences between the input descriptors. You can find more details of how to construct the modified energy and apply the discrete solver to optimize different functional map energies in our paper. In this example, we show some results of using our discrete solver to minimize the area preserving energy and the conformal energy. We initialize the functional map from random pointwise map. In the blue box, we show the results of projecting the optimized functional map obtained from continuous solver. For simplicity, we will call it continuous solver directly. In the red box, we show the results of our discrete solver. The top row shows a pair of boxes that have the same surface area. We can see that for this pair, optimizing the area preserving energy using our discrete solver leads to a better map. The bottom row shows a pair of boxes that are conformal to each other but with different surface areas. In this case, optimizing the conformal energy using our discrete solver gives a better map. This shows that our discrete solver is energy aware, which means the problem relaxation and the discrete optimization considers the input energies. As a comparison, although the continuous solver can decrease the energy values during the optimization, the optimized functional map does not correspond to a high-quality pointwise map. In a short summary, in this work, we propose a simple discrete solver that can optimize different functional map-based energies. It returns a proper functional map that corresponds to a pointwise map in good quality. It also achieves lower energy values compared to the standard continuous solver. Our discrete solver also has two practical applications. The first application is to replace the multiplicative operator proposed in 2017. The multiplicative operators are designed to constrain the functional map to be proper in a soft way. The second application is a new refinement method that applies our discrete solver to minimize a combined energy, including bijectivity, orthogonality, and Laplacian commutativity from both directions. In the following slides, I will show some results and quantitative evaluations. We first evaluate our discrete solver in minimizing different functional map energies. This test is performed on 50 sheep pairs from small animal dataset. Here we show some commonly used functional map energies. We then compare our discrete solver D to the continuous solver C by measuring the energy values on optimized functional map. We report different statistics of the energy values in this table. We can see that our discrete solver achieves much lower energy values than the continuous solver. Here we show some qualitative results. We use the continuous solver C and our discrete solver D to minimize the Laplacian commutativity energy from random initial maps, shown in the top row. We can see that the pointwise map obtained from our discrete solver, shown in the bottom, is more accurate and visually smoother than the continuous solver. Here we discuss the first application of our discrete solver. Our baseline is a multiplicative operator proposed in 2017, as highlighted in red. This term is constructed from input descriptors and is designed to guide the optimization towards proper functional maps implicitly. In our setting, the proper functional map is addressed as a hard constraint. Therefore, we no longer need the multiplicative operators. In this image, we show an example of Faust human pairs and compare these two settings. We can see that our solution not only achieves lower energy values, but also outputs a more accurate and smoother pointwise map as shown in the right. The second application is a new refinement method that applies our discrete solver to a combined energy. We compare this new refinement method to other post-processing methods on Shrike-Nighting challenge. The results show that our method achieves better accuracy and bijectivity than the best baseline zoom-out with comparable runtime. In summary, we propose a discrete solver that can efficiently optimize different functional map-based energies. This leads to two practical applications. The first one is to replace the multiplicative operators that are commonly used in the functional map pipeline. The second application is a new refinement method that combines different functional map-based energies and outperforms the baselines in Shrike-Nighting challenge. Our work still has some limitations. For example, our discrete solver has few theoretical guarantees, although we observe that it works very well in practice. Also, for some functional map energies with complicated formulations, our reformulation strategy might not work directly, and more advanced solvers might be needed. In the future, We plan to explore different coupling terms and investigate different pointbus map recovery techniques, such as single-hole algorithm. You can find our demo code in GitHub. Thank you for your attention.